Welcome to the University of Sydney's Warren Centre Forum on Digital Energy, a focus on virtual power plants. The forum today is all about virtual power plants, or VPPs. The forum is a collaboration between the Sydney University Warren Centre and the Sydney University Centre of Future Energy Networks. The forum is also sponsored by Nokia, so thank you, Nokia. The Warren Centre is an engineering think tank. The Warren Centre brings industry, government and academia together to create thought leadership in engineering, technology and innovation. Sydney University Centre of Future Energy Networks is an internationally recognised research centre specialising in the fields of energy and power networks and intelligent grid technologies. I will be the MC for today. I'm Andrew Collins. I'm a member of the Warren Centre and a graduate of engineering from Sydney University, albeit a few years ago. So just quickly, we have three wonderful speakers today. Professor Joe Zhu is the head of School of Electrical and Information Engineering at the University of Sydney, and he is involved with research collaborations exploring the future of digital energy systems, focusing on distributed energy resources, microgrids and virtual power plants. Dr. Greg Abramovich is the head of virtual power plants at AGL. He will share AGL's journey in the distributed energy resource landscape, insight into the virtual power plant market and technology innovation, the value in VPPs, as well as the importance of prioritising the customer experience. Martin Horsk is the Asia Pacific energy leader for Nokia. He will present on the future trends of the energy system and the role of digital communication and internet connectivity, or the Internet of Things. Martin is actually based in Singapore, so it's a very early start for Martin, so we certainly appreciate his participation this morning and Nokia's sponsorship. Before we proceed to the presenters, I would like to call on Dean Willie Zwanapol, Dean of Sydney University Engineering, to provide some opening remarks. So Dean Willie, if you could please provide those opening remarks.
Thank you. Well, first of all, I'd like to join in welcoming all of you to this event. I see there's 55 people on the call, and it's quite a good turnout. So I think it's nothing surprising about saying that digitalization is changing every industry, and that energy is part of that. So as response to this, I'm also trying to reorganize the faculty a little bit with more of a focus on digital in general, and digital energy systems is clearly a key part of that. I'm not an expert in it, although I was trained as an electrical engineer a long time ago, but it's sort of pretty clear that this can and will radically reform the energy industry from basically a commodity industry to an added value service industry, delivering improvements in quality and efficiency, reliability, and so forth, and also incorporating renewable energy in a more flexible way. So today, I mean, it's already introduced, we'll be talking about virtual power plants, which is key focus area of Joe Zhu's group. We're also pleased to have Greg Abramovich from AGL and Martin Hauske from Nokia in Singapore with us, who will also shed some light on the subject. I'd like to thank Martin, first of all, for getting up so early, and secondly, I'd like to thank Martin and Nokia for their sponsorship of this event. Not only is we're sort of at the beginning stages of a relationship with Nokia that I'm really looking forward to, Not only are they sponsoring this event, but we're testing, or we're going to be testing some Nokia equipment, 5G technology and IoT capabilities in Branko Vucicic's lab. So with that, let me finish. Let me thank you all for attending, and I hope you will find the content of this event very interesting. Thank you. Andrew, back to you.
The video is thank you, Willie. Hopefully you can hear me. I'm not sure if you can see me. Hopefully you can.
Yes, I can hear and see you.
Thank you. We're used to gremlins in Zoom, so I'll apologise firstly, and hopefully not have to continue to apologise as we go forward. The first speaker today is Joe Zhu, head of the School of Electrical and Information Engineering. Joe, if you could proceed, please.
Hi, good morning, ladies and gentlemen. The topic I'm going to talk about today is digital energy systems, challenges, opportunities, and technologies. Well, this is a list of contents I'm going to present. Basically, I'm going to focus on challenges, opportunities, and technology of VPP technology. So, as we all know that electrical power generation based on renewable resources have been developed to cope with fossil fuel depletion and climate change. Australia is rich in renewable resources and also at the forefront of uptake of distributed energy resources globally. Australian Energy Market Operator, AEMO, predicts that power supply will consist mostly of renewable energy resources by 2020, with more than 20% coming from small-scale distributed energy resources. By DERs, we mean distributed generators plus energy storage plus a management system. So DERs are installed on the distributed level and operated by EMS to provide grid support to improve the electricity quality and efficiency. In parallel, DERs can be installed together with electrical vehicles in the future and also loads in for specific customers such as households, clubs, buildings, and offices, and behind the power meters, for the objective to improve electricity quality, improve the reliability, and reduce the energy cost, in particular electricity bill. So the advances in DERs and the microgrids have enabled customers to generate and to sell electricity. So we call them prosumers, resulting in two-way energy and information flows. However, the existing power grid technology developed in the early 20th century cannot support this kind of significant change. The rapid development of digital technologies enabled a revolution in energy management. Electricity can be managed at the level of aggregated DER and microgrids to function as a single entity. We call it the virtual power plant in power network and energy market. So this forms a part of a digital energy system. The objective of this white paper is to assess the current situation, identify the challenges and opportunities, and provide a better understanding of digital energy systems. We aim to trigger collaboration between the research community, industry, and the government agencies, as Australia seeks to find an effective integrated solution to the nation's distributed energy resources. Well, when the massive DERs and the microgrids generating all the electricity and the sale in the electricity market, the current or traditional centralized power system becomes decentralized. And in the electricity market, so there will be a two-way electricity market, become a two-way electricity market, as shown by this diagram here. You will see that the aggregator can deal with retailer, and also the customers or prosumers deal with retailer to sell and buy. So a significant challenge for this kind of situation is to balance the intermittency of large-scale renewable power generations, especially when the government introducing the renewable energy zones. So this will require larger-scale energy storage. Well, larger-scale energy storage is possible, but it is still very expensive for the time being. So a smarter way is to reshape the demand to increase the power system resilience by using distributed energy storage in DERs and microgrids. So in this way, if we put them all together in the virtual power plant in the form of that, then intelligent intelligent energy management system using demand flexibility for system operation would be possible at a new level. Another challenge is that the energy market lags behind many other sectors. Say, for example, say Amazon, Alibaba, Google, Facebook, Uber, and Airbnb use digital technology to run platform-based business to bring together sellers and buyers. So for this, when the microgrids, DERs, when the prosumers, when they try to generate and also to sell, the current way they have to sell to the retailer. But with this kind of technology, so we can create a sort of a P2P energy market. So the prosumers can sell to their neighbors, can buy from their neighbors. So in this way, not only say produce economical benefit, but also we can actually reduce the line transmission loss as well. But this kind of P2P support, market does not solve the problem of network support. So for the network support, then we have to take advantage of so-called bidirectional power flow four-quadrant operation capability of power electronics. So the power electronic user, we can use this kind of power electronics to increase the system resilience by controlling the power flows. And also we can aggregate all these DERs and the microgrids in the form of VPPs or virtual power plants. So in this way, we can provide not only say network support, but also market operation, optimal market operation. Well, this diagram illustrates schematically a VPP, which basically connects geographically dispersed DERs and MGs by IoT networks. Then the VPP manager system, which is in edge cloud computer, can coordinate the optimal network operation by so-called bidirectional power flow four-quadrant operation, but on the other hand, can coordinate market operation simultaneously. So in this way, we can achieve high system resilience, high reliability, efficiency, and economic benefits simultaneously. Well, VPP concept has attracted great attention of academic researchers, industries, and governments worldwide due to its distinctive advantages of providing optimal network and market services simultaneously. Various VPP pilots are in operation in Europe, USA, Japan, Singapore, and Australia. So operated by energy management system, these VPPs can provide network services for technical benefits so-called TVPPs, annual market services for commercial benefits, so-called VPPs. But the current VPPs are small in capacity and suboptimal in coordination because the system optimization has not been realized, and thus cannot fully exploit what DERs and MGs can offer. Well, challenges to realizing digital energy systems include a holistic system-level optimization approach to achieve simultaneous optimal network and market services, adapt market rules and policy requirements to accommodate new technologies, large-scale communication networks with strict latency, reliability, and bandwidth requirements, and cybersecurity solutions. Along with this, the opportunities are the innovative VPP concept can be an effective solution to decentralized, scalable two-way digital energy system. The new concept VPPs can greatly strengthen power grid resilience so as to enable integration of large-scale renewable power generations, for example, renewable energy zones. To address these challenges, we propose pilot projects to test and advance new technologies. Then next, I would like to talk about market design and policy framework. For DERs and microgrids that integrate into VPPs, we consider three types of market architectures. The first one is centralized, which is the existing one. The second one, decentralized, which deal with various sorts of DERs and prosumers. They can trade with the wholesale market. But on the other hand, if we introduce P2P, then we have to consider distributed market architectures. When transitioning the existing market frame of centralized power system structure to a decentralized power system structure, market design and a policy framework will incentivize DERs and microgrids or VPP investment, which will address the energy trilemma, increasing economic efficiency, reducing carbon emissions, and improving grid security. Digitization underpinned by ubiquitous communications, big data analytics, AI, and blockchain technologies will support network companies to work together with DERs and microgrid aggregators, or VPPs, and the retailers to facilitate the disruptive energy markets. Also, support the distribution energy markets with full prosumer participation. The Australian Energy Market Commission, which is a rule maker, has recently introduced two essential rule changes. One is wholesale demand response mechanism that will enable the market participation of VPPs to bid directly into the whole market. This is very, very important to encourage VPP. And the 5-minute settlement rule that will provide a better price signal for investment in fast response technologies such as batteries and the VPPs. In parallel, the Energy Security Board proposed 7 market design initiatives, including a long-term approach towards two-sided market arrangements and the initiatives to facilitate DERs and microgrid market integration to enable DERs and microgrids or VPPs to participate in multiple markets and the service provision. To implement the holistic system optimization approach, the VPP coordination platform is based on large-scale hybrid cloud system architecture. Optimally dispatching massive DERs and microgrids in a VPP requires a distributed optimization approach, which finds a solution iteratively in conjunction with the VPP platform. Since distributed computing is independent of problem size, a VPP can readily aggregate millions of DERs and microgrids. The digital orchestration of massive DERs and microgrids require a data-driven approach supported by data analytic tools such as machine learning, data mining techniques, and deep neural networks. Electricity network constraints should be introduced into the DER and microgrid coordination for optimal power flow in the wholesale market. This approach has been successfully trialed in the recently completed ARENA-funded Brunei Island battery trial, in which Sydney University team has played a significant role. Then next, I would like to talk about communication network. The data-driven VPP management will require reliable, pervasive, and scalable communication networks for large volumes of data to be collected, shared, and analyzed across the digital energy systems among VPPs, DERs, and microgrids, grid control center, and the electricity market. As shown in this one, basically, it consists of 3 levels: device level, enterprise level, and the balancing group level. Then VPP platform sits in the cloud on the top level. Then this table shows the latency requirements of VPP technology at different levels. So as you can see that device level needs the lowest latency, whereas the balancing group level can be, or enterprise level can be longer latency. Then among all this, then the VPP communication network needs to enable multiple applications with very diverse performance requirements. The current 4G cellular network cannot support different applications on single network infrastructure. Therefore, the 5G network should be considered. The 5G network with the capability of network slicing, SDN, and edge computing are the most suitable to support multiple digital grid applications and sustain ultra-high reliability, low latency, security, scalability, and interoperability. As 5Gs can operate in the licensed, unlicensed, and dedicated spectrum, VPP could be supported by their own private networks, which could provide a better performance, security than the public networks. In VPPs, the cybersecurity is really important as it has very various points for possible entry and information leak. So for VPPs, the key concerns include rigorous identity and access management to prevent unauthorized user activity, enhance multi-layer network security focused on wireless security, and a robust personal information and privacy management to protect sensitive and individual user data. Identity and access management is a challenge in VPPs. A possible solution to increase cyber physical security is to use lightweight security protocols in DER aggregation. So AEMO recently developed a cybersecurity framework to access the cybersecurity maturity and the security profile of all energy participants. Well, next I would like to talk briefly about our expertise. Our school has world-leading expertise in power systems, power electronics, Internet of Things, telecommunications, AI, and optimization, and thus is uniquely positioned to address the challenges of digital energy systems. Our multiple disciplinary team has a history of successful industry collaboration, including the Smart Grid, Smart City project, and the award-winning ARENA project consort. We have partnered with Nokia to develop solutions for the digital grid of the future. Our cutting-edge research expertise is supported by a state-of-the-art VPP testbed, which is a flexible hybrid cyber-physical power system model for emulating VPP network and market operations under different coordination and trading strategy and algorithms. It will be used to trial the developed solutions and translate them into business cases for network companies, retailers, and DR aggregator and technology providers alike. Well, this is a photo of the VPP testbed. In conclusion, an unprecedented opportunity exists for the Australian energy sector to decide on how it will transform to meet this current and the future market needs. Change will no doubt be disruptive, but it will occur, as it did with new business models in other industries. Some changes is in fact already occurring in the sector. Electricity distribution is moving to a two-way market, and digital technologies are supporting changes to digital energy systems, while fresh commercial opportunities with prosumers are being investigated through new modeling. The University of Sydney Centre for Future Energy Network and the Centre for IoT and Telecommunications are at the forefront of this change, and the world leaders in new modeling of the power and IoT industries. We invite you to join us on this journey for change. So if you have any need to contact us, well, this is the contact detail. You're welcome to communicate with us. Thank you. Any questions? So I hand it back to you, Andrew.
Thank you very much, Joe. That was a very, very good presentation, and we are taking questions at the end. The second speaker is Dr. Greg Abramovich, Head of Virtual Power Plants at AGL. Greg, if you would like to proceed with your presentation.
I will do. Thanks very much, Andrew, and thanks, Professor Swanepoel and the Warren Centre for the opportunity to talk here. It's obviously a you know, as a University of Sydney alumnus, kind of a particular honour to participate in this this event. I'm just trying to share my screen, but it's not offering me the opportunity to share my desktop. Is there does somebody need to make me a or kind of give me the opportunity to present? Ah, there it is. Bear with me.
Hi, Greg. I've just made you a co-host.
Great. Thanks. That I should be able to share now, and you should be able to see my presentation in a second. Is that all working?
Yes.
Yep, great, excellent. Look, thanks again, everyone, for the opportunity to present. As Andrew said at the start, I'm from AGL, who are a retailer and generator in the Australian context. We've been involved in the VPP industry or market, I guess, since 2016, when we launched an arena-funded program to kind of test the capabilities of VPPs. So I'd like to talk a little bit about our journey in VPPs and distributed energy, beginning with our projects in 2016, and then working through how we participate at the moment and what offers we have for customers. I'll give a little bit of kind of technical context around what it is we do and how we do it, but with a particular focus, I think, on consumers and how we view the consumer experience as integral or critical to the success of VPPs. So, I spoke a little bit about that project in 2016. In early 2016, we started putting together or developing a project to test a scaled version of a VPP. Particularly, VPP is a definition that could encompass multiple things, and I'll talk a little bit later about all the different kinds of assets that could participate. We were particularly focused on residential energy storage installed behind the meter at customer homes and businesses. You know, in that context, in South Australia, particularly where we focused on launching that VPP, there was a lot going on. There was a transition of the existing generation fleet. There was a lot of baseload generation that was starting to exit the market. There was an increasing penetration of wind and a little bit of solar as well. There was some quite significant volatility in the wholesale market. And that was starting to force out some of that baseload generation. So it was very much a focus point of a transitioning energy system and an opportunity to demonstrate the capabilities and the opportunity of a flexible resource such as a VPP. So the intent of the project was to show how you know, VPPs could be used as that flexible resource to manage wholesale market price variability. You know, as I said at the start, AGL is both a generator and a retailer and has quite a complex portfolio of both load and generation in which to manage. And so we see VPP as another tool that can be used within that complex portfolio. South Australia obviously had the highest penetration of renewable generation in the NEM at that stage, and I think at that stage had the second highest penetration of rooftop solar. This is pre the Sister Black event that happened in Australia, but I think that, sorry, in South Australia, but of course that brought into focus the criticality of a well-managed and you know, kind of orderly integration of renewable generation, increasing renewable generation, and particularly renewable generation like rooftop solar that is driven primarily by customers and a desire for customers to participate in the energy system. This project, you know, in a nutshell, the intent was to create a virtual power plant of 5 megawatts, you know, using 1,000 controllable batteries in homes and businesses, you know, installed behind the meter. We wanted to concentrate those in metropolitan Adelaide, which we did. We have a higher concentrations or pockets of higher concentration in very specific parts of metropolitan Adelaide. But effectively those 1,000 are spread across metropolitan Adelaide. It's worth considering back, you know, to the time of early 2016, you know, when the project was developed, there were a number of other VPP projects that had been announced, but this at 1,000 units and 5 megawatts, which is quite a sizable kind of scaled chunk of generation or kind of packet or parcel of generation or load curtailment at least. You know, was quite a significant step. It was, in our view, a step into a scaled arena, and you know, significantly larger than had been done, particularly with residential storage, you know, certainly in Australia and elsewhere in the world as well. The intent was to facilitate further integration of intermittent renewable generation, again, using the flexibility of these assets as part of a flexible portfolio or portfolio that has both significant load and generation and the need for balancing flexibility between those. We wanted to demonstrate improved network stability. Now that could be code for a whole number of things. Certainly we wanted to demonstrate network services and how VPPs could be used to demonstrate network services, and we have done that. We've published, I think it's worth saying now, a number of ARENA reports as part of our ARENA funding. You know, we've done these, we've published knowledge sharing reports. Those are all available in the ARENA website, and there'll be another one that will be published later towards the end of this year, which is the final one that we'll be doing for the project. We wanted to also demonstrate increased solar self-consumption by consumers installing a battery and reduced energy bills, but then also how you can create additional value. A lot of consumers would participate or buy solar or invest in a battery because they want to self-consume more of their solar and they want to make bill savings, but by coordinating the dispatch of a large group of batteries, can we create additional value over the top of that that can then be shared back with customers? And that is really kind of foundational in our thinking about VPPs, and that they need to be able to create additional value, not just shift around value that already exists. And certainly that additional value needs to be shared in a very transparent way with customers. ARENA were keen at the time when they provided the funding to us that this would be a catalyst for the development of the Australian VPP market. And indeed, we've seen a number of other VPP or larger VPP projects be announced since our announcement in 2016, and that's a good thing. We're at the early stages of what was then a nascent market, which now is still a young but growing market, and it's important that that others that there's kind of competition in this space, and that others see the opportunity, and that there is enough value provided by these opportunities that others would seek to get involved. And then also, I'd just like to, kind of gratefully acknowledge the funding that we got from the Australian Renewable Energy Agency as part of their Advancing Renewables program, which partly funded this project. I've spoken about, kind of creating additional value, and when in many VPP presentations, we hear people talk about different value streams or value pools or stacking value pools. In our mind, this is the three major value pools to be stacked. One is the consumer value pool. That is their self-consumption. We'd estimated at the start of the program that the average consumer, with the average solar export and the average household load, and we had to use averages across metropolitan Adelaide because we weren't sure who was going to participate in the project, would have achieved about $500 of bill savings just by consuming more of their solar and installing that battery. On top of that, they also got a high quality, AC coupled energy storage system. There are a number of different hardware options that were available through the course of the program, which is obviously now closed, and we've installed all of those 1,000 batteries. Most customers paid about $3,999. We did shift the price around a little bit. Certainly it started a little bit lower than that and ended a little bit higher. But that was a massive discount on what the with the standard costs, exclusive of any other kind of state or federal subsidies, would be for a battery at that time. So customers get to buy in, in exchange for them purchasing a battery from us and getting it installed. We asked them to be a part of our VPP for 5 years and a part of that experimentation and testing and journey with us. Then there's also wholesale value. So there's obviously wholesale energy, and then also frequency control and ancillary service market participation. So, again, as a retailer with both a generation and a load book, we were looking to use those assets or aggregate and control those assets in a way that could create wholesale value. We also did a number of tests on how these batteries could provide an FCAS service or participate in FCAS markets. I'm pleased to say that today AEMO is actually running what's called the VPP demonstration program that allows behind the meter storage systems to be used in contingency FCAS markets, all 6 contingency FCAS markets, and we are registered in South Australia in those markets. And so these systems, a large proportion of these systems are actually providing those balancing services today, literally as we speak. The last one is network value. And this one remains, in our view, nascent in some respects. Certainly there's an opportunity. We've done a lot of tests to show that aggregated batteries in a very specific part of the network can provide quite accurate and meaningful peak demand management services, voltage management services at that low voltage circuit level. I say nascent because you really do require, and we've spoken about it in some of our reports, a critical mass of systems to be able to provide that service. But we certainly see that as a growing opportunity pool for VPPs in the future. Obviously, if those services provided to a network could be used to reduce or defer augmentation costs. There we go. I wasn't expecting the animation. There's the animation of, or a slide that summarizes our current VPP offers. So for a customer that buys a battery from us, and we recently launched battery sales and installations in states outside of South Australia. So we started that in South Australia and moved to other states. We offer a $1,000 discount in the upfront cost of a battery, in addition to any other state subsidies that might exist, or other support that might exist for batteries, where we're selling them. And in exchange for that, again, we ask the customers to participate in our VPP for 5 years. But we put really clear, transparent guardrails on that participation. So in the example of where we sell a customer a battery and provide that $1,000 discount, we also say that where we orchestrate your battery, the impact that that orchestration is going to have on your bill is going to be less than $50 every year. And we give customers visibility of that $50. You know, we have quite a sophisticated mechanism for calculating that likely impact on the customer's bill of orchestrating their battery in a certain way. And we'll shortly be showing customers that through digital channels, through an app or you know, through their online account, so that customers can track that. And we think that that's foundational to building trust with consumers for what should really be an exemplar of the future energy system, with, you know, two-way flows of energy and value, and you know, customers participating in an energy market. For customers that already have a battery, we have what we call our BYOB, or bring your own battery offers, where we offer customers a, you know, $100 sign-on bonus and $180 per year for participation. There we limit our coordination or control of those batteries to 30 events per year. So again, really clear kind of guidelines and guardrails and transparency on how exactly we're controlling those batteries. So I'll put aside the all of the consumer offers for a minute and just talk a little bit about how we view technically VPPs. You know, Joe's given a really great explanation, which I think accords with what we're proposing as well. We see, you know, as I've said, VPPs is this exemplar of this evolving two-way energy system. You know, VPP doesn't really have a definition per se. I think everyone, you know, thinks of VPPs perhaps in a slightly different way. We take a very broad approach to VPPs. It could include home batteries. In future, we expect that, you know, electric vehicles will be considered. We see large C&I batteries. We see deferrable loads, particularly at large C&I sites, as part of a broader VPP, and then other controllable or flexible assets. So you know, with a focus on demand side management, you know, assets that are flexible and can be controlled. We see this virtual power plant as this intermediate piece that has both technical, commercial, and customer engagement aspects, and then serving, you know, on the left-hand side, a whole lot of different markets or value pools. We started out our journey with the residential battery VPP, but of course that's expanding over time. And I'll talk in the next slide just a little bit about how we've architected our system, particularly from a data and control perspective. So, you know, I've kept it generic in terms of actual, you know, brand names, but starting at the bottom, you know, we see batteries installed in consumer homes, where we're talking about batteries. It could just as easily be, you know, aircon control or hot water heating control, whatever demand side management device or resource we're talking about. Those typically talk through a vendor or a proprietary hardware vendor device cloud, down to the actual devices themselves, and then AGL talks to that vendor cloud. So, you know, to put a brand to it, we have Tesla Powerwall 2s as a part of our fleet, and we talk to the Tesla cloud, which then talks to those individual batteries on sites. You know, just as Joe mentioned, there are different layers of control that are affected, you know, that are most effectively managed at different device layers. For example, you know, those contingency FCAS services that some of our storage systems are providing, those are best managed by the device locally. It's a mode that is set on the device locally, rather than you know, having to have the challenge of latency and signals moving backwards and forwards, you know, between an overall or between a kind of a high level cloud. We use a company called Imbala as that DERMS layer. Now DERMS again is kind of a variable term that could mean a number of different things. You know, we use in this context DERMS or VPP control layer interchangeably. They then, Imbala, who are a US-based technology company, they speak to those individual device clouds, and they are the levers and buttons that affect the control that we want managed. So we then talk directly to Imbala to say, we want a certain proportion of the fleet to do a certain thing at a certain time, based on, you know, either an agreement we have with the network, you know, to provide a service, or perhaps in response to something that's happening in the wholesale market. So these are obviously, all of these communications are joined via API nowadays, and so are effectively cloud-to-cloud integrations. It's worth noting also, though, that you know, in the top left-hand corner is AGL. We we both talk to Mbala, so that control layer, but we talk to the device layer as well, to ingest as much data as we possibly can, so that we can, first of all, have a good understanding of what the fleet is doing at any given time. We have quite a sophisticated time series database that we use to do that, and you know, we layer a number of functions over that data in that database. We also want to provide customers visibility of how we've controlled their battery, what impact that's had on their bill, and where their battery sits at the moment, you know, and how it's performing effectively through a number of digital channels. But you know, importantly, where these are interfacing or we're using these assets in a real life market context, it's incredibly important. First of all, that we're bidding realistically about what availability we've got, but then also that we are you know, making it clear to customers how we're actually using their assets and what impact it's having. This is the final slide, and just to wrap up, we're often asked the question of where we see the virtual power plant market going and what opportunities there are for growth in virtual power plants. And so these are the kind of the 5 fundamental areas that we see that will underpin growth in this market. So the first is supporting customer drivers. That is recognizing that these are primarily customer-owned assets, and customers have their own reasons for investing in these assets. And this, you know, this extends to EVs, it extends to all sorts of, you know, kind of devices that are installed in the home, primarily, you know, to support the customer's home use or solar self-consumption use. There are different models for VPP. Sometimes they're centrally owned and they're, you know, kind of provided through a PPP arrangement with customers. But we see the bulk of particularly energy storage systems today being installed and paid for by customers. So I think a recognition of that and recognizing that customers don't probably, you know, well, not probably, customers don't buy batteries just to be a part of a VPP, but it is certainly an additional value that can be provided over the top to help pay back, and you know, customers do enjoy being a part of a broader network that is helping to support the grid. I've said it a number of times in the discussion, but building trust with customers, you know, it's easy to say, but it really requires a level of visibility and access to their own data and understanding about what is going on and how their battery is being used. And it's really fundamental to growth in this area. We see a lot of consumer surveys being done about, you know, we do them ourselves. We speak to our own customers a lot and ask them, you know, how they feel about how we've controlled their batteries in certain contexts. And the feedback, you know, is consistently that they want to understand why their battery is being used. And even the customers that kind of don't really want to understand why or aren't interested in the technical nature of it, certainly want visibility to know when it has been controlled. And you know, we think that's, again, foundational to growth in this area. There needs to be value that's provided to consumers. You know, through these programs, it's not about creating additional value that is then consumed by the VPP aggregator. The intent of these systems is to make our customers our clients as well, and to be able to provide some of that value back. There is power in numbers. There's power through aggregating these systems and creating additional value, provided that is shared back with customers. We also see a need to support market participation of these devices, and you know, we really commend AEMO in particular with their VPP demonstrations program and allowing, you know, energy storage systems under a trial arrangement to be able to participate in these frequency control and ancillary services markets. And we'd like to see more of that. There's a lot of market reorganization being thought of and designed at the moment, and you know, the greater participation of these devices and the more value that can be shared back with customers, you know, the more growth we're likely to see in these markets. And then there's, you know, the last one is really carefully managing that grid edge interface. And again, you know, Joe spoke to issues like cybersecurity, understanding the physics of the local grid, and you know, finding an appropriate balance of allowing customers to participate, to create value and receive value, but then also not curtailing the potential value that those devices can provide, and making sure that customers are appropriately compensated for any services that they might be providing to the network. So with that, I'll wrap up. Hopefully I'm dead on time, and you know, thanks again for listening. I'm happy to answer any questions when the time comes.
Thank you very much, Greg. It was a fantastic presentation, particularly describing the customer experience. And you were definitely on time, so thanks again. Look, the final presentation today before we go to questions will be Martin Hauske. Martin is the Asia Pacific Energy Leader for Nokia. And Martin, if you would like to present, please.
Thank you very much, Andrew. And this is really a hard act to follow. Thank you very much, Greg and Joe, for sharing this very insightful presentations. As you can tell from my accent, I'm German, and I would like to highlight some of our experiences in Germany. And previously, I worked with a company called Kisters, who has deployed one of the largest VPPs with over 400 megawatt. So it's becoming already in Germany the last line of defense. But so VPP for me is already one step ahead. This one, I fully agree with Greg. Batteries are here to stay. The prices have come down. When I was partner at Accenture, I talked about 1 megawatt hour battery was $1 million. Now we are well under 200,000 within less than 7 years. So prices are in rapid decline. In Australia, wind farms are cheaper to produce than fossil fuel power plants, driving to an economic. Even Texas has now, I think, more jobs in wind farms than in oil. Having said that, with the story leading to a very variable input, as Greg and Joe mentioned, the output is pretty nasty. So if you have that kind of an output and trying to store everything in batteries is virtually impossible. On the other hand, with the current regulation, particularly restricting the distribution companies' role on the network rather than the market, I see that it's one of the biggest challenges, and I would be more than happy to share some of those experiences. Sometimes regulators and politicians see their way a little bit simple, like in Germany. The joke is that they think Germany is a copper plate that you can plug in solar anywhere without any physical constraints. Where are we in Germany? We are already in 2019 at 55 gigawatts. So the outlook shared here with 63 by 2020 is already nearly reached. Solar also already near 50 megawatt in 2019. So we are seeing a massive oversupply. So we have over 40 days now in the market with negative power prices, vast oversupply, but at the same time with the dearth of fossil generation, similar to what Greg shared in South Australia, the fossil units go off stream, the nuclear goes off stream, then you don't really have a baseload anymore. And this leads to an escalating situation where we have extreme prices on the positive as well as on the negative side, which is great for VPP if we have a variable load, if we can participate in this, and how do we share the spoils of that, but then also how that will help to mitigate some of those market extremes. The second point, besides the energy price, I want to highlight is network constraints. Germany now, so Joe, Germany is taking the experiment even further with almost 47% of renewable generation out of total generation, leads to massive constraints. The constraints in particular, Germany implemented renewables, and here on the right side, I want to highlight the German geography. We have the brilliant idea, we have wind in the north, but then BMW factories in the south. If you don't have insufficient transmission capacity, obviously you cannot use the wind. Same scenario in the south, lots of solar, but then you have got still Volkswagen up here, same problem. So without sufficient transmission capacity, networks are constrained, and merit order has been violated over 15,000 times now. It's a daily occurrence that you have to redispatch large generators, leading to incremental cost. At the same time, my example of Germany being a copper plate, this has led to massive investment on the distribution grid to accommodate those solar farms about 20 kilometers away from the substation. while we could see much better management. So Greg, these are some of the same points that you mentioned. If we use volt-var control more actively, we could actually stabilize the grid through active participation. Where are we in Germany? This is 2019. Germany finally almost managed to take down the European grid. In June, we reached prices of 37,000 per megawatt hour versus normal prices around 60 euro. At the same time, our CO2 emissions are still not where they were supposed to be. And one of the reasons is, while electricity industry has been trying their best, we shut down the nukes, but new segments like transportation has barely budged. People drive a lot, as you know, those crazy Germans. Buildings have become slightly more efficient, but also only marginally. So we really need to do a cross industry play, not only see the energy system, but see the other systems that are actually producing CO2. This chart you have seen, Greg, it's a nicer version of that. So where are the pools that we can get? The energy, and I'm beyond the consumer, I see particularly commercial real estate, who manages government buildings, who manages universities, but also larger energy consumers like companies that have CHPs. They typically don't utilize all the capacity of their CHPs. So how can we integrate those players, share value? Then network investments, as I mentioned, transformer augmentation in order to accommodate all the solar. Battery is one way, but then also we have got the EVs coming. If we look at the new fast charging of 350 kW, if we want to do that at peak, we take down the transformers. Besides the spot market, I see also the secondary reserves as a key point. Having secondary capabilities enables a line of defense. And these are some of the simulations from German condition. We've got all this beautiful renewable coming, but unless we can balance it, we will have to expand the network actually. And the way to do it is the flexible consumers cross-link with VPP to balance production and demand. So same conclusion that you came to, Greg. The markets that in Germany we are addressing is future, the control, physical balancing, as well as integration of PVs. Also, Germany has not yet set up the grid market, being one of the potential opportunities. I want to talk about the case study I mentioned. This started with over 30 assets. This allowed the VPP to have a nice spread, but also besides the customer satisfaction being profitable, because you always have to look at how much money are you spending on the VPP versus how much money can the consumer or the participant make. One German utility in Munich, they started a raffle, got many new subscribers, but if you make 3 to 5 euro and you spend 50 per consumer, that's not a good business. So looking at how can we have the right returns. It's just a refrigerator, probably it's not going to be worth it to invest all this technology. This is the scale of the market with reserve. Minute reserve is 400 megawatt already. So over 400 megawatt being dispatched out of a German spinning reserves of 1,800 megawatt. So this shows you the scale that this VPP has already reached, which is up to a fourth of the spinning reserves. So having that kind of massive scale becomes critical, and this only enhances Joe's point about security. If some hacker were to hack into the VPP and then pretend that we could deliver and then not deliver, it would take down German grid. So security is very critical, 27001 in particular. Where do we position the VPP? This was the chart that Joe also showed already, that it is the linkage between the SCADA side as well as the market side, linking, balancing the grid and adding a flexibility layer to the TSO side. But as Joe mentioned, with the rise of DERs, we believe that is also relevant for grid side. In particular, when we have high penetration of renewables like South Australia or in Queensland, how will the distribution grid look like if we have got nearly 100% renewables? This project was done in southern Germany called Web to Energy, mid-sized scale batteries, some wind parks, some PVs, some CHPs. The point I want to highlight is if we have constraints, we can move 44 to 46% of consumption. This is something that, as Willie pointed out at the outset, changes the basic model that we are operating under. We are no longer a distribution company, but we become a platform provider. And how do we balance supply and demand flexibly? If there's some emergency, up to 100% can be moved. And from a commercial benefit, I talked about value pools, up to 8% of peak power can be shaved. When we think about the investment in distribution grid in particular, this is real money. This is the investment that we need the fewest moments, but asset utilization is really poor. So if we can reduce the peaks system-wise, it's a great benefit. Next step, and thanks Joe for your great collaboration with Branka and Gregor, is 5G. And some of those leading parts that are starting to be deployed is, for example, San Diego Gas and Electric's system called FICE. And FICE is a system. FICE is a system, micro PMU. One second. I hope you can see it again. 1 second. I had some small system issue here. A micro PMU that enables inverter control. Like I mentioned in the initial chart, how can the inverter control enhance better integration of DERs? In Germany, we are actually wasting 9% of DER output currently because the grid cannot take it. So the curtailment is quite severe, which is a waste of customers' investment, but also a lost opportunity for cleaning up the grid. So we use synchrophaser data for feedback control. Also, we can do drones and robots for field work. So this is really the next stage. How can we do micro control, as well as with massive IoT, which 5G was designed for, more devices to be integrated smoothly. Batteries is definitely the first one we can do today, but refrigerators, air conditioners, those units, how do we do it in a commercial viable way? We must have scalability to handle that. This shows the next possibility where we got closer to the devices, having very tight distribution integration to a DSO. So when we fast forward to the grid of the future, traditionally the SCADA system has several thousand points. Now when we look at the devices I talked about, smart meter, with smart inverter, we've got EV charging, we've got all those devices at the pole, as well as the DG, that leads us to a utility of 4 million customers having more than 12 million devices in this field. This is already a scale that traditional SCADA and ADMS cannot handle. So we have a blank spot. How can utilities scale to that level commercially viably? This is not somebody sitting in front of a laptop trying to manage it. One example in the field is San Diego Gas and Electric. They saw the same challenges, peak load, overall load dropping by 5% because of customer producing their own power, renewable hitting 50% of their generation. And then the government is being California pushing very hard for green. At the same time, EV charging was happening, causing spikes. And how do we become member of this new system? So instead of rejecting, it was many utilities started to do, they say we embrace it. We become an enabler of this new world. And what does it take to do that? First of all, we need to increase our backbone capability, lower our cost to communicate, so they integrated IT and OT with an IP MPLS network. Then second, as I talked about the number of endpoints they saw versus 3.6 million customers, they saw 200,000 endpoints. So 200,000 endpoints being impossible with traditional means. Since it's mission critical, we don't do RF mesh, the speed and latency is not sufficient. So we went with private LTE. Thanks to that, we have better integration of renewables, more revenue from services. Gee, we can make money outside of selling electricity. By adding value, we position ourselves as DSO and become a platform provider. The other example, this is Germany again. After that experience last year, the utilities got together and said, this cannot go on like this. We need to have better capabilities, particular ability to have black start, because we may eventually take down all of Europe with all of our science experiments. Nokia, what does Nokia provide? Nokia set up a model to manage distributed energy with alarm monitoring, fault, etc., data collection. This uses our IoT software capability and enables efficient and scalable control. In Australia, we manage already VHAs, we manage TPG's network. So we have got experience in managing extremely large telco networks, and this is basically another instantation of that. Applying it to VPP. In VPP, we have got the grid operation. How do we integrate it securely? How do we support the protocols? Nokia supports the security, end-to-end encryption, etc. And this allows then via LTE to manage the devices in a secure and reliable way. One example that I want to finish with is our architecture talks about managing all the devices. We collect them via the field area network. Then we have got a data platform called Impact to collect the devices, and we have got an analytics platform called Spacetime on top. Then we manage it in our network operation center, so it is tightly integrated to scalable modeling. And we manage in particular large devices that can back up the grid. This is a linear generator, really revolutionary, allowing exactly as Greg said, to lower costs while increasing reliability, as Joe pointed out, and then really signing up for SLAs, particularly for rural places. Australia's 250 to 300 minute SAIDI outside of major cities, which is just not acceptable in days of COVID-19, where people want to work from home or business needs to run.
Thanks, folks.
Bye. Thank you.
Thank you very much.
Bye.